atmospheric transport for greenhouse gas flux inversion using machine learning. So I'm gonna start with showing this work from Brian McDonald's back in 2014, where they kind of like looked at the effect of spatial resolution on road emission fluxes. So they started with like a very coarse resolution, about 10 kilometer or so, and as we can see that we can't really see like much of the emission patterns pretty well here, and it's very hard to like do source attribution. But if we go like a bit finer, so around 4 kilometer, we start seeing like some of the special patterns. For example, probably like this could be like a freeway or something. And when we go even finer, so about at 1 kilometer, we are able to like resolve freeways clearly from the background. And if we go even finer, around half a kilometer resolution, even we can see like the arterial roads and resolve them as compared to the background. So what I'm trying to kind of like emphasize here is that the high resolution information is kind of like required to accurately attribute local and urban sources of GHGs. So now moving to estimating emissions. So we have this equation. I'm pretty much sure like a lot of you have already seen this equation. Um, and yeah, you'd just like to relate observations to emissions. And so we have this equation y equal to hx plus b where, uh, just, okay, yeah, so y is the observation, x is the emission or state vector, which we typically solve for, b is the background, and h is the Jacobian, which kind of like represents atmospheric transport. As such, if we look at like each row or any single row of this h matrix, which signifies like the influence of all the sources on a given measurement. And on the other hand, if we look at any column of this H matrix, which signifies like impact of a single source, but on all of the measurement. And looking at like a physical significance. So let's say we have a measurement site somewhere here, and somewhere far we have a emission source, a car in this case, which is emitting like some CO2 molecules or something. So in order for these CO2 molecules to be recorded by this station here, they need to be transported, and the transportation is done via atmosphere. And this is what like this H matrix here represents. And each row of this H matrix is also known as a footprint. And as such, if we like plot this footprint or a single row of this H matrix, it will look something like this, which is called a footprint. Here, this star mark is the observation site, and these arrows are the instantaneous direction of wind. And this shaded region here shows the sensitivity or like content of this H matrix. And what that means is that the darker shade here, which is in the upwind direction, has higher influence, or like a source which is here in this darker shade on the upwind side will have a higher influence on this particular measurement as compared to a source which is in this lighter shade, which will have like almost zero influence because it's in the downwind direction. And we typically use like Lagrangian particle dispersion models to compute these footprints. And these footprints are kind of like sensitive to the region upwind as well as the input meteorology. However, the input meteorology can change with time, right? So do like these footprints. So here I'm showing like how a footprint for a single location can change throughout the day. So you can see like there is like significant changes because the methodology can change throughout the day. So what that means is for every measurement, we need a footprint. And especially at high resolution, computing these footprints can be computationally expensive. For example, like about 1 kilometer resolution, it can take up to 1 hour, even for like a urban scale of like 400 or 500 kilometer or so. And as such, this computational cost increases linearly with the number of observation and can be a huge bottleneck for like dense observing systems such as like satellites or surface-based networks. So what I am kind of like focusing on during my PhD research is, can we emulate this source receptor relationships? Or in other words, can we just like use machine learning to compute these footprints on the fly? So for that, I have like generated a large amount of training data. So about like 500,000 training examples across the whole corners, just to like get some training data to train our footnet model. So here we use like two different sampling strategies. So first one is like the gray dots that you see in the background, which we just like randomly sampled across the whole corners. And the second one is like these stars that you see. They are also like randomly sampled locations, but they are just like 400 kilometer by 400 kilometer subdomains or like small regions. And within each of these 400 kilometer by 400 kilometer regions, we further um, kind of like randomly sampled about 2500 receptors at the center. So here I'm showing like one of these like 400 kilometer by 400 kilometer region. So the kind of like the idea behind using these two different sampling strategies was with the gray dots, we are kind of like covering the whole corners. So we have like a much larger area to generalize on. And with these star locations or enhanced representation from a single subdomain, we are like spending enough time on a single location to learn like more complicated, complex features, for example, like variations in metallurgy, change in topography, etc. And all of these receptors that we sampled across like 2 years, so 2020 and 2021. And we like uniformly sampled across like all months of year, all days of the months, as well as all hours of a day. um, yeah, so that way we kind of like see different seasons, different hours, and those kind of things. And yeah, so this is like the 500,000 receptors, and then we generated footprints using stilt for assuming it as to be a surface measurement, and then X stilt for assuming it to be like a column averaged measurement. And then we trained like two different models. Um, and so overall, we had like about 30 terabytes of training data at 1 kilometer spatial resolution on a 400 kilometer by 400 kilometer boundary. And so this was like our entire training set. We also created a subset of this training data, which was only like sampled in year 2021. And the idea behind here was like just to check some generalizability or out of sample capability of the footprint model. So here what we did was like we identified two domains. So domain A corresponds to San Francisco Bay Area, and domain B corresponds to Barnett Shale in Texas. And what we did is like we just removed some area around this domain. So like most of the California here and much of Texas here, so that we kind of like ensure that there is no um, correlation between like training data and this evaluation domain here, either in spatial or temporal domain. And we use like these two domains for our downstream evaluation. So evaluations in like flux inversions. And for domain A, we use like beacon surface network. So hourly CO2 data there, and did like some flux inversions. And then for domain B, we used tropomy methane observations, and did like flux inversions there as well. Okay, so now talking about our footnet model and its architecture. So before talking about architecture, I just like first wanna talk about our aim here or goal here, which is to simulate a footprint, right? That our model should be able to output or compute a footprint. So if you look at like any conventional or like traditional physics-based atmospheric transport model, what they do is like they use some input methodology like winds, surface pressure, etc., and then use some mathematical equations to kind of like solve for trajectories while conserving mass, energy, momentum, those kind of things. So the idea here is pretty much same, that we also use like some input methodology, as well as some features that we compute on the fly. um, so here we use like different input methodology, for example, like zonal and meridional winds at 10 meter, which is a good proxy for surface winds, PBL height, which tells us like how much mixing is going on in the system, and then surface pressure, which is also a good proxy for topography of the region. And then we use like these three methodology data on like for the both surface footnet and column footnet. So here surface footnet is to compute footprints for surface measurements, and the column footnet is to compute footprints for column averaged measurements. And for column footnet, we also use like some other vertical information, for example, like winds at different vertical levels, like 850 and 500 hectopascal, as well as temperature at 850 hectopascals. And these are like all the variables that we typically like load from archived methodology. So we used her here, which is at 3 kilometer, and just like regraded everything to 1 kilometer. And simultaneously we also like compute some features on the fly. um, for example, like Gaussian plume, which is reversed wind based, because it's a back trajectory model. So here is an example of a reversed wind based Gaussian plume. It's very important feature for our model, because it kind of like first it tells the model where the observation site is located, because otherwise everything else here, the methodology data is like continuous fields. But here the origin of this plume is the measurement site. So that's much more easier for the model to understand where to start the footprint from. It also gives like an initial guess, or to kind of like where to start the footprint structure from as well. So it gives like both the observation site location as well as an initial guess. Second, we also use the linear distance from receptor. So linear distance of each grid point from the receptor site. So as well as the exponential distance for each grid point from the receptor site. So the idea behind like using these distances was, because as we move away from the receptor, the footprint values decrease, right? So just to kind of like create a balance between near field and far field, we use these distances. And additionally, we also use a Gaussian plume network mask, which is just like a binary mask for um, different Gaussian plumes as we like add vector particle, and as it moves in this in this domain. So how like the Gaussian plumes at different times and different locations would look like, and then just like using a 0 1 binary mask there. So these are the inputs, and the output is a footprint. And we have used unit plus plus architecture, which is a variant of the original unit model that we were using in our like previous papers. So these black circles here, these are so this is again an autoencoder model. So like based on encoder and decoder. So these circles here on the left side represents encoder, and the circles here on the right side represents decoder. So encoder kind of like does downsampling to identify important information at different like scales, and then use that information. Decoder uses that information to compute a footprint. So these black circles here are the original unit model, and the only difference between like the original unit model and unit plus plus is we have some extra layers in the middle, especially in the skip connection. So in the original unit model, we directly had just like this black connection here from this x00 to x04, and then from this layer here, or this block here, to this block, and this block to this block. But what we did here is we just like added some extra blocks in the middle, and we connected them through different blocks here. So for example, like this block here is connected through this block, and this block. This block here is connected through this block, and this block. So this way we are just like doing much more well connection, and that kind of like ensures that the information flows very smoothly from the same scale or same level, as well as downsampled or zoomed in level in this architecture. And we kind of like notice that this gives us much more physical structures as compared to the just like the original unit model. So we just like decided to use the unit plus plus here. So remember, our training data is like about 30 terabytes or so, with a 500,000 training examples or footprints. So just like one single training iteration on this on a single GPU with like these 500,000 footprints will take about 2 days. And we typically like train for about 80 to 100 iterations, depending on when the validation loss is stabilized. So that would be like very time consuming, right? So for that, I used a distributed data parallel framework provided by PyTorch, which is like very much similar to MPI. And the idea here is like that it just uses same model replica on different GPU devices. And we can just like those devices while training talk to each other to make sure that the model is stays same across all of those devices. So how that works is we have a data loader which has like all of these 500,000 training examples, and what it does is like it creates different shards of these data, and it provides like different batches to different footnet replicas on like different GPU machines or like different servers. And so we start with like similar footnet architecture or like similar same model replica on all of these machines, and but we just like provide a different batch to all of them. And then we perform a forward pass, which is to like compute a footprint given like whatever weights that we initialized. And then we also have the ground truth for all of these local batches, right? So we compute gradients with respect to that local ground truth, and the local output from all of these footprint on the GPU machines. So that way we have like local gradients, but the gradient, for example, like in this GPU 3, will be different from the gradients here in GPU 2 and GPU 1 and GPU 0, because they have different batches of the data, right? So what we do afterwards is we allow some communication between these GPUs to synchronize the gradients. So how that works is it uses some reduce operations to just like sums up all the gradients and take an average, and then after that it just broadcasts that synchronized gradients back to all of these GPU machines. So then that way we have like the updated model, which is same across all of these machines, and then we do the backward pass to train our model. So this way it kind of like ensures that the all of the models are all the model replicas on different machines are kind of like same across the whole training iterations. And this is how like the distributed data parallel works. But yeah, this was very nice, and I used about like 15 GPUs or so and was able to like get the training time within 10 days using this framework. And yeah, one more thing for training that I wanted to talk about was the mass conservation. So this was like a clear limitation of our footnet model, that typically like physics-based models conserve mass very easily. But for example, like if you look at Stilt, which is kind of like a wrapper on high split, right? That we use some input methodology and then run high split model to compute trajectories for different particles, and then we look at like those trajectories for the particles and see when they are closer to the ground or like below the PBL height, and then that way we compute a footprint. So if we look, there is like some kind of like discontinuity, right, between the input methodology and the footprint directly, because there is a step of computing trajectories in the middle. And once we have the trajectories, then we just like look at when they are closer to the ground to compute a footprint. So there is no like direct relationship or mathematical relationship between input methodology and the footprints that we can use directly to like constrain the mass conservation. However, if we look at like the footprint formula, which is I guess like directly proportional to the mass of the air parcel or something. So from there we just like try to put a light constraint on during our model training. So what we did was we just summed over all of the footprint values here in like our predicted footprint, and then compared them or looked at the mismatch or disagreement with respect to the ground truth, and then normalized it with respect to the ground truth. And then we just like edit this term in our loss function along with the mean squared error, and used a penalty term here, alpha, which is to just like scale this second term. And to get the optimal value for alpha, we did like some sensitivity tests where just like I just took a small subsample of the training data and then trained different models using like different alpha values here. Um, and so as we can see that like the x-axis is here is the alpha values, left y-axis is the validation loss, and the right y-axis is the percentage footprint sum difference, or this term here. And so as we increase the alpha or this penalty term, we see that like the percentage footprint sum difference try to like decrease. which is because like this term here starts becoming a dominant one in the loss function, and the model while training try to like minimize this term here. But as we increase alpha, the validation loss also increases. That is because the main training kind of like happens because of the mean square error loss function. But as we like increase alpha, this term here, the second term becomes more dominant, and that kind of like performs or causes the suboptimal learning. So what we want is kind of like a balance between these two terms, and then we just saw that like here at alpha equal to 1000, we kind of like get a better result, and both of these terms minimized. So we just like use the alpha equal to 1000 for our model training. And talking about feature importance, so I did some permute and perturb tests. So how that works is within a given sample, we just like shuffle one feature at a time. So for example, like if I have 8 examples, so I just took like the Gaussian plume from first example and randomly assigned it to example number 5, and Gaussian plume from example 2 to example number 6, and Gaussian plume from example number 3 to example number 1, and so on. So this way, just like randomly shuffled them and then looked at the performance, um, and like how much drop in the performance we get with respect to like the initial performance. And the higher the drop is, that means that feature is like more important. So here I'm showing like top 6 features for our model, and um, Gaussian plume is like the most important one, which makes sense, right? Because if we shuffle the Gaussian plume or doesn't like compute it right, then we are kind of like essentially telling the model where to start the footprint origin from a wrong place. So it's gonna like compute a footprint at a different place, and that would be completely wrong. So and it's also like tells the initial structure. So that makes sense that why it's kind of like ranked higher. Then we have surface winds at time of measurements. Again, it's kind of like an important feature because it drives the advection. Then linear distance, which kind of like balances the near field and far field. And in our previous paper, we kind of like did some test on how the performance in flux inversions improves dramatically while like when we add the linear distance as an input feature. And then again, like some winds, but 6 hours before the time of measurement are also important. And if we look at like the column footnet, we kind of like have similar features here as well. And this is like a strong indication that the training is here for like both of these model is like consistent, and model is probably like learning the physical relationship between the input methodology and the footprints. So moving forward, just like comparing the footnet predicted footprints with the stilt model for surface footprints and X-tilt model for column averaged footprints. So here I'm showing a footprint which is a ground truth computed using stilt in Massachusetts, and here these arrows shows instantaneous direction of wind. So we can see that like wind is coming from southwest and pretty much like constant, and as a result we have a, Gaussian plume looking footprint, and our model was like able to identify this feature pretty well. And then this is another example, like close to Lake Michigan shoreline. So this is Lake Michigan here, and this is the Michigan state. And we can see that the footprint is kind of like hugging the shoreline of the Lake Michigan. And our model was like able to identify this complex feature as well. However, if you see like the footnet predicted footprint is much more smoother as compared to the external footprint, which has like sharper gradients. And this is another example in Utah, which is mountainous terrain, so much more complex transport there, and our model was like able to identify this feature as well. And this is another example in Texas, like a flat topographical region. However, it's like a very interesting example because here we see like very sharp boundaries um, in the still footprints, but on the other hand, the footnet footprint is like much more smoother. And we have noticed like that this has implications, especially like in the flux inversions. Even though like this kind of transport from the stilt is very accurate, but only when like the input methodology is also accurate. But in reality, we have like biases in the input methodology, and which can kind of like change the footprint structure, and still is like highly sensitive to those biases in the methodology. But on the other hand, we notice that the footprints are much more smoother and kind of like offers less sensitivity to those biases, and can be kind of like that can be helpful in the flux inversions. But this was not our final goal, to just like compute the footprints. Our final goal is to see how these footprints computed by footnet perform in a flux inversion. So for that, going back to this equation, I just used Bayesian inference to get this closed form solution for the posterior estimate of the emission fluxes. So here we have like some prior fluxes, and then we add the second term here, which is like a gain term multiplied by the mismatch between the observations and model simulated observations. Here B is the prior error covariance matrix, and R is the observation error covariance matrix. So we kind of like kept all of the parameters of inversion same, except for changing the Jacobian or H matrix, and just like replaced it with the footprints computed using footnet model. And then we just like estimated fluxes and then compared them with the fluxes computed using stilt based footprints. So I'm going to show here results for like domain one, which is San Francisco Bay Area. So we use like hourly beacon CO2 measurements here. And so the top row here shows the physics-based ground truth. So using stilt footprints. The first column shows footprint cumulative influence, and this white contour shows like the 60th percentile of the influence from the footprint. So what that means is the top 40th percent of the influence for like all of the measurement is within this white contour here. And the second column here is the average posterior CO2 fluxes. And we can see like some of these structures pretty well. For example, like high emissions in the Bay Area and freeways. And the third column shows some independent validation. So here we just like randomly put aside some observations and did not use in the flux inversion, and then just like compared the observed CO2 on the x-axis against the predicted CO2 on the y-axis. And these are some of the like for example, like correlation coefficient is 0.65 and mean squared error is 493 ppm square. And then we kind of like perform this exercise again, but using our footnet model. But we trained like two different models. So first one with California in the training data. So using like the entire training set of 500,000 examples. Um, and then we noticed that the footprint cumulative influence is much more kind of like wider, and that's probably because footnet footprints are much more smoother, right? So it's covering a bigger area. But if we look at the average posterior CO2 fluxes, they looks pretty much similar. For example, like we can see the emissions from freeways, higher emissions in the Bay Area, sink in like north of Bay Area, and those kind of features are pretty much similar in both of the cases. But if we look at like the independent validation, we see that there is a better agreement between the observed CO2 and predicted CO2. For example, like correlation coefficient is much more higher, and mean squared error is also about 15% or more improved. Then I trained another model without using California data in the training data. Also, like this inversion was done in year 2020, but we only used here data from 2021. So we did not use California data, as well as we did not use any data from like the same temporal domain, just to like do some true out of sample test here. And then we performed like this exercise again and computed the or did the flux inversion, and then looked at the summary, and then noticed that like here also we have like similar results, and the performance is like better in this case as well. So we have like mean squared error improved with respect to the ground truth, as well as the correlation coefficient. And this was like very surprising because Footnet was like trained on stilt, but it still like performs better in this particular case. Yeah, so there was kind of like surprising to note there. And talking about some current work that I'm doing. So I'm currently like investigating how we can use FootNet to better understand tropomy observations. So currently, the inversion frameworks are limited to much more coarser resolution, and but FootNet computes footprint at kilometer scale resolutions very easily. However, using tropomy has like another issue, that the tropomy ground pixels are also coarser, so about 5 by 7 kilometers square. So to account for that, here I'm showing like a tropomy single ground pixel, and what I did was I just divided this whole tropomic ground pixel into like smaller kilometer scale subpixels. And since footnet can compute like footprints pretty fast, it's like less than a second for a single footprint. So I just like computed footprints for all of these subpixels at kilometer scale. And then once we have like footprints for all of these subpixels, and if we just like average them over, that gives us a footprint at kilometer scale, but for the whole tropomic ground pixel. And this approach is very interesting because if we like zoom in on this kilometer scale footprint for the whole tropomic ground pixel, we kind of like see very interesting features. For example, like higher sensitivity towards the upwind boundary and lower sensitivity towards the downwind boundary. So essentially, there is just like a gradient somewhere in this tropomic ground pixel, and what that means is that the we are able to kind of like resolve much more finer scale features, even though our tropomic ground pixel is like much more coarser through this approach. And this has like about 80 times more computational cost because we need to like compute 80 times more footprints in general for like all of these like kilometer scale subpixels, right? But since we can compute footprints using footnet very fast, so it's still much more feasible to do with footnet. And this approach also allows integration with other satellite products, including point source imagers, to kind of like account for detected methane plumes also. So here I'm showing like US oil and gas basins. So these are like some of the major basins across the whole US, and we can fit like the footnet boundary pretty well. So footnet can only like present compute footprints for like 400 kilometer by 400 kilometer domain, and many of these basins are like much more easily kind of like fit inside this domain. So currently, I am focusing on Permian. So we are using like two different flux inversion domains. So the first one on the left side is for Delaware Formation, and the right one is for Midland or Spraberry Formation. And we are like doing the inversions for these two domains separately, and then gonna like combine the results together. So if we look at the data for one single domain, so like solving weekly emissions from May 2018 to December 2025, we have about like 383,000 observations in total. But the state vector is like much more larger, so it's about 60 million for like the whole spatial and temporal scale. And computing like prior error covariance matrix is just not possible for this one. So we have to use Kronecker product decomposition for our prior error covariance matrix there. And here are some of the preliminary results for the flux inversion for the first like the first boundary, which was the Delaware formation. Yeah, these are like very fresh results, but yeah, I just did the so currently I just only did the monthly runs, so 1 month at a time, because it was just like even making the whole Jacobian was much more memory intensive, and so I'm just like still trying to figure out computationally efficient ways to do the whole inversion at once if possible. Um, and this is the time series of the emissions for this Delaware formation, from like weekly emissions and also 4 week rolling average, starting from like May 2018 to December 2025. Some of the features seems like consistent from previous work. For example, we see like very much kind of like similar or flat emissions, especially in this time period. but there are like some interesting features as well. For example, like this sharp decline and then sharp increase. I don't have any answer for like what was the cause as of now. But I also need to like do inversions for the second domain first and then try to like see results after like combining them. So I guess I'll have like better results soon. But yeah, these are like some preliminary flux inversion results. Okay, so to summarize, FootNet is a generalized emulator that can compute footprints for both like surface as well as column averaged observations, and it can match or sometimes exceeds performance in flux inversions as compared to STILT or XTILT. And um, we also like compute surface sensitivity at finer scales compared to like Tropomi, coarser spatial resolution. And currently, I'm working on conducting high resolution methane flux inversions using Tropomi and Footnet in Permian. And I also plan to like jointly solve for fluxes and boundary conditions or backgrounds as part of the flux inversion. Yeah, thank you so much. And let me know if you have any question.